Hello, my name is Dan Brunner, and in this video, I'll be going over how to solve problem 11.008 from Chapter 11 in the Fundamentals of Mass and Heat Transfer textbook. So in this problem, we have a shell and tube heat exchanger with a total of 2 shell passes and 8 tube passes. Water is being fed through this heat exchanger at a rate of 45,500 kilograms per hour. We should note that we need to convert that to kilograms per second when we do any math in our problem. And this water that's passing through the heat exchanger is heated from 80 to 150 degrees Celsius. We should also note that the total surface area of this heat exchanger is 925 square meters. So we also have hot exhaust gases that enter at 350 degrees Celsius and exit at 175 degrees Celsius. And so this water is being heated up by the hot exhaust gases. And we can assume that the hot exhaust gases have the same thermophysical properties as air. So here's what we're given. We're given the mass flow rate of the water. Again, I converted right away to kilograms per second from kilograms per hour. We're given the inlet water temperature and outlet water temperature. I converted them to Kelvin, although in the problem, when you're using the temperatures, you're mostly just using them as temperature differences. And so the Celsius to Kelvin conversion doesn't really matter. But the average water temperature, when you average these two numbers, is about 390 Kelvin. That'll be important for when we find the properties of the water using table A6 in the appendix. We're also given the number of shell passes and tube passes. And we're given the inlet and outlet temperatures of the, we'll call it air, in Celsius. Again, I converted to Kelvin. And finally, we're given the surface area of the shell and tube heat exchanger. In the problem, we're asked to find the total heat transfer coefficient, U, in watts per meter squared Kelvin. And to do this, since we're looking at a shell and tube heat exchanger, we can use the effectiveness NTU method. To solve the problem, we'll be using the following assumptions. We're assuming that we've reached steady state conditions in the heat exchanger. There are constant fluid properties. So as the water is flowing through the heat exchanger or the air, the temperature variations of either fluid do not affect the properties of the fluid. We're also going to assume that the heat exchanger has thin tube walls, and so the area that the water is exposed to is equal to the area that the air is exposed to, and that area is equal to the total surface area that we're given in the problem statement. We're going to neglect radiation heat transfer, and so the net radiation is negligible. We're going to say that there's negligible heat loss to the surroundings, so the only heat transfer that's occurring is occurring between the water and the air. We're going to neglect any changes in kinetic and potential energy for either fluid. There is negligible wall friction or fouling of the walls inside the heat exchanger, and we're going to assume that we have fully developed flow conditions. So what this problem really boils down to, no pun intended, is really just plugging numbers into the equations you can see on this slide and ultimately working your way towards a final solution. And so the equations that I have listed here include the heat transfer rate for this heat exchanger. We have the heat capacity terms, where this CH is equal to the mass flow rate of the hot fluid times the specific heat of the hot fluid. And this CC term is equal to the mass flow rate of the cold fluid times the specific heat of the cold fluid. There's this ratio as well, where you have the minimum heat capacity divided by the maximum heat capacity. And that'll be important in the problem. We're also given the effectiveness um, formula, which is equal to the heat transfer, which we can solve for using this equation up here, using either the cold side heat capacity or the hot side heat capacity, divided by the maximum heat transfer rate. And that maximum heat transfer rate is given by the minimum heat capacity times the temperature difference between the hottest temperature in the heat exchanger and the absolute coldest temperature in the heat exchanger. We're also then going to need to solve for the number of transfer units, this NTU term. And if you look at table 11.4 in the textbook, you'll see a bunch of heat exchanger NTU relations. And these formulas are all for the shell and tube heat exchanger option in that table. And since we have 8 tubes, we can go through and see which formulas are applicable for that number. Or sorry, we're going to need the number of shells, not the number of tubes. And so when we go ahead and look at how to solve the problem, I started off with the heat transfer coefficient. This U term is equal to the minimum heat capacity times the number of transfer units divided by the surface area that heat is conducting through. And when you look at this equation, what you ultimately need to do is find the values of each of these terms. So we're given the total area inside the heat exchanger that the fluids are transferring heat through. And we're not given the minimum heat capacity and we're not given the number of transfer units. And so ultimately, we need to solve for both of these terms, and then we'll have our total heat transfer coefficient. One thing to note is that we have the mass flow rate of the water, which is the cold fluid in this scenario, but we don't have the mass flow rate of the hot fluid or the air in this scenario. And so because our heat transfer rate is equal to the hot side, which is equal to the cold side, we can use the fact that we can solve for the cold side heat capacity and use that to solve for the hot side heat capacity. So I went through and solved for the cold side heat capacity. I've got my mass flow rate of the water times the specific heat of the water. That specific heat, again, is found at the average temperature of the water using table A6 in the appendix. And once I found this cold side heat capacity, I could rearrange this equation up here for the heat transfer rate and solve for the hot side heat capacity. And when I compare the cold side and hot side heat capacities, I see that the hot side is smaller than the cold side, so that must be the minimum heat capacity term. So that's one of the terms solved for. Now we have to worry about the number of transfer units. And this is a little bit more complicated, not necessarily more difficult, but more complicated because there are a lot of equations given in the table I referenced before that we will need to use to solve for the number of transfer units. So starting off, we can solve for the effectiveness, this epsilon term, again, by dividing the maximum heat transfer rate by the actual heat transfer rate. And the heat capacity terms here you see cancel out because I chose to write the actual heat transfer rate in terms of the hot side. And so since the minimum heat capacity is equal to the hot side heat capacity, those terms cancel out and you're just left with these temperature differences. Again, note that the maximum temperature difference isn't the maximum temperature difference of either fluid. If you compare the fluids, it's not the temperature difference or the larger temperature difference between the fluids. It's the hottest temperature of either fluid minus the coldest temperature considering either fluid. And so the hot side inlet temperature is the hottest temperature in the system. The cold side outlet temperature is the um, coldest temperature in the system. And so when you go through and solve for the effectiveness, you get a number of 0.648. And once we have the effectiveness, we can go ahead and solve for this F term. Ultimately, this F term will be used to solve for this E term, which will be used to solve for the total number of transfer units. And so going through and solving for this F term using the ratio of heat capacities and the effectiveness that we just solved for, we get a value of 1.451. Looking at this E term, plugging all the values in, the only new value we need is this effectiveness of the first shell pass. We can solve for that using the F and ratio of heat capacities. And so when we go through and solve for this E term, we get a value of 3.03. That number, I don't think, is really supposed to mean anything to you, but it's just a way for all of these relations to work out to give you an accurate number of transfer units. And so now that we have our E term, we can solve for the number of transfer units for the first shell pass. We get a value of 0.637. And then there's this relationship between the first shell pass and the total number of transfer units for the entire system. You simply just multiply the number of transfer units for the first shell pass by the number of shells. And in this system, we have two shells. We're given that in the problem. And so our total number of transfer units for the entire system is 1.27. So now we have all of the terms we need to solve for the total heat transfer coefficient, U. So when we plug in the minimum heat capacity, which is the hot side heat capacity in this case, and the number of transfer units, we get a total heat transfer coefficient value of 29.53 watts per meter squared Kelvin. And that is how you solve problem 11.008. Thank you.